Thank you. So I will speak loudly. Hopefully you can hear me. Yes? Okay, thank you. And of course, it's a just tremendous honor to come here to tell you a little bit about the story of the past 2 decades of the atomic clock development, in particular on neutral atom side. And we'll actually mix in a little bit of the history. We heard the name Jan Hall, and so you will hear a few of these names throughout my lecture in terms of how the field has been developing so fast and what's the prospect of the next few years or decades of this field, where it's going. So, there's one important area of physics as we are all attached to or attracted to the fundamental physics. And I always think of, as a human society, the way we understand nature is by building two scopes. One's telescope, one's microscope. And because the microscope allows us to understand things on a very small scale, high energy physics, there are still many mysteries in that field. Telescope allows us to understand the macroscopic structure of the universe. And the third area, which is a really interesting area right now, the quantum complexity, with traditionally many-body physics, phases of matter. Actually, out of this now, quantum information science that connects AMO, atomic molecular optical physics, and condensed matter physics, it really forms a new frontiers of a measurement science. And this is where I'm coming from, by learning sort of a quantum complexity many-body systems to push the frontiers of measurement science forward, which can come back to help us building, in some sense, a new frontiers of telescopes and microscopes to understand fundamental physics. And hopefully, throughout my lecture, I'll give you a little bit of sense of that. So clock is a telescope and a microscope in itself. If you have a really fantastic clocks that can measure time down to 10⁻²1, and of course you can use clocks like that to directly map gravitational waves. Making a clock to be so stable or so precise or accurate will allow us to set limits on this elusive dark matter, where we don't really know the origin of which, whether it has any force connecting outside of gravitational manifestation. We can, in the future, maybe build a network of clocks. This would be the largest interferometers that humankind can think of building, and use this to really probe deep into the universe, the nature of the dark matter's dark energy. But at the same time, it shines down to the Earth. Of course, it's a microscope that will allow us to understand the relativistic geodesy, the underground mass, underground water, and so on, because space and time is intrinsically related to each other. Excuse me. So let me tell you to the very, very basic level, how do we build atomic clock? And the build of atomic clock really relies on this incredible success of quantum. And quantum has both certainty principles and uncertainty principles. Going back to Niels Bohr, when you start to describe a new atomic model as electrons moving around the nucleus, now we can think of these prescribed electronic orbitals are the nature's best timekeepers. Those atoms were made for billions of years. And every single atom, if you did your measurement right, they will tell you the same time. If you measure the energy difference between two electronic orbitals extremely well. The difference between this generation of clocks versus the traditional generation of clocks that still defines the time, although the redefinition of time will be coming soon based on this new generation of clocks, is that in the old generation, you're looking at energy level difference by flipping the spin of electron, while the new generation of clocks relying on an optical energy connection between two electronic orbitals. And that gives you much faster pendulum that you can think of to use this to measure time. But of course, there's a real important uncertainty principle in quantum mechanics. Some people would say the only reason quantum mechanics is different from classical is the uncertainty principle, which is in some degree, I completely buy that, because that's how it limits our measurement precision. This is where we do secure communications, where we can build quantum computers and so on. In fact, it's all related to this uncertainty principle. And simply understood is, you can have eigenstates of Hamiltonian, but when you put it into a so-called quantum superposition between two eigenstates, well, there's an energy difference between the excited state E and the ground state G. This energy difference is a phase factor that's moving around, and this is exactly the time I want to measure. But on the other hand, when you put an atom in the superposition of the two states, and you try to measure where you are after a certain time that's evolved, you wouldn't be able to know. There's a fundamental uncertainty principle that when you try to finally measure where the atoms in the E or G, you don't have a priori information. So that's the uncertainty principle. This uncertainty principle limits how well you can build an atomic clock. So what I'm doing is I have a macroscopic laser that has a phase coherence. It's a field of electromagnetic field, happens to be in the visible range that we can see this laser light. And this laser light probes the atom by preparing atom in coherent superposition. And you follow the phase of this atomic evolution for a while, and then you go on to make a measurement of asking how many turns you have made on this quantum pendulum. And you're trying to measure this phase difference, E times T. And because of the uncertainty principle, every time you flip, you're preparing superposition, you make a measurement, there's uncertainty built in. So the reason that we want to use many, many atoms is because each pendulum has this uncertainty. If I have many, many pendulums, my uncertainty will be reduced. The so-called standard quantum limit is 1 over square root of how many measurements you can make, assuming the quantum noise is completely pure white, and that's a square root. The more particles you have, the better the measurement precision. Later on, I will tell you a little bit of a story of quantum entanglement. And the quantum entanglement comes to the fact that if you can make all these particles to be entangled such that not every particle, when you make the quantum uncertainty measurement, is independent. You only have one copy of noise out of n copies of a signal. Then the signal to noise ratio goes, it was 1 over n. And this is where the entanglement can help you tremendously, especially if n is a large number. And this is what we are chasing after, so-called Heisenberg limit. Today, most of my lecture will be talking about without the entanglement, but there's a couple slides will tell you about the entanglement, how entanglement can play a role, and is playing a role. And I want to emphasize one more thing is, this atom that we picked, the strontium atom, belongs to the second column of the periodic table, has 2 valence electrons. And one specific property that makes it very attractive is the atomic clock states have a very long lifetime, 120 seconds. And this is the optical frequency. Okay, this is a color that you can see with your eye, 698 nanometer, and yet you prepare atom in coherent superposition, and it will live there for 2 minutes. And we'll show you some of the recent experiments where we can now start to show the quantum coherence can really be demonstrated in our laboratory, where you prepare a quantum object with hundreds of thousands of atoms, and they live there for this macroscopic amount of time. So this comes to, in some sense, a summary point. The modern push of quantum metrology is really trying to meet from, the precision frontier with the quantum frontier. What I mean by that is you're looking for quantum systems that has very long coherence time, something that's oscillating with hundreds of, millions of billions of cycles per second. And this is in the hundreds of terahertz regime, 10 to the 15th hertz, let's say. And yet the lifetime is 2 minutes. So the quality factor, you let this pendulum start to swing, it will swing 10 to the 17 times before it decays away. That's what they call the quality factor. This is a tremendously good quality factor. And the quantum science is all about having macroscopic quantum coherence and protect it and use it for something. The other part is I want to build as many particles as I can in the quantum system so that I can push down the standard quantum limit. And this very modern push is using many-body states. You can see that we can now create artificial lattices using optical interference patterns, putting atoms one by one, and start to use optical optimization of quantum resources, including entanglement, to enhance this beyond the standard quantum limit. And so in some sense, you can see this as a very easy to understand concept. But the technology of pursuing these things really represents the modern atomic and molecular optical physics over the past couple of decades. And in fact, it's quite interesting to look at the list of these things. The quantum control has now enabled this very high quality optical transition to be probed. Laser technology has moved forward over the past 2 decades, where in our laboratory we can demonstrate optical coherence can approach almost a minute. Frequency comb, as mentioned earlier in the introduction, that allow us to synthesize electromagnetic fields. Quantum gas, Bose-Einstein condensate, degenerate Fermi gas, allow us to control many body states. So no wonder if you look at the historical chart of the clocks after World War II, This blue dots represent microwave clock. This red dots represent optical atomic clock. And you can see the slope of the progression is very different because of the technology is just more superior with using optical domain. And this is not stopping here. I can tell you, for example, over the past few years, in 2019, we achieved this level of precision, 3 times 10 to the minus 19 measurement precision, accuracy of mid 10 to the minus 18 or so. Over the past 4 years, we were able to push the measurement precision to the mid 10 to the minus 21. And use this fantastic measurement precision, we can further evaluate all the systematic uncertainties of the clock and having accuracies now at 8 times 10 to the minus 19. And you can see this progress just still continuing. And I think at this point, my lecture today will tell you a little bit about how we can leverage the quantum many-body resources to connect to, reach 10 to the minus 19 and beyond on the measurement precision. We can discuss what's the usefulness of such a fantastic precision. But certainly, in order to push to this pathway forward itself is very interesting because AMO physics is now connected to condensed matter physics, is connected to some level to particle physics, and the interesting areas of impact you can have of gravitational physics that I mentioned briefly later. And so it represents sort of an interesting convergence point of physics where technology development gives us new opportunities of probing physics beyond perhaps even, may I dare to say, the particle energies that's beyond the access of the current collider technology. And so let me just briefly mention of the control of light, since that's obviously an important piece of technology in our optical atomic clocks. We know that electromagnetic wave spans many, many decades of the frequency spectrum. The visible is actually a small part of this vast, gigantic landscape of electromagnetic spectrum. And if my laser happens to be at the color of 698, 700 nanometers or so, and it's carried by a simple diode laser technology, diodes that we use to listen to DVDs and watch DVDs and so on. And this laser emits a light with a bandwidth of a few hundred megahertz. This is about 1 million zoomed in from the entire rainbow color of the visible spectrum. And it's clearly too broad to probe atomic spectroscopy. So we zoom in another factor of a million. This is a technology actually from my thesis advisor, Jan Hall, in the 1980s. They developed these incredibly laser stable technology, powerful laser stabilization technology where you can see a piece of very low expansion glass and it has 2 mirrors attached to it. And they tested all the laser locking technologies on this cavity where later on the same technology was used to see the gravitational wave of LIGO. But this, after another million times zooming in, that's still way too broad to probe this narrow atomic transition with such high fantastic quality factor. And we have to develop actually yet another laser technology. This is thanks to now almost 2 decades of collaboration between my lab and PTB, the German Standards Laboratory in Braunschweig. And we developed this crystal-based, silicon crystal-based cavity now allowed us to achieve very, very narrow laser spectrum, for this case at a 1.5 micron with 8 millihertz line width. So coherence time is on the order of several tens of seconds. If you translate this into coherence length, this would be if you had a laser spanning the distance between the Earth and the Moon, you can actually shine this laser back and forth 100 times. Imagine you build a microsecond interferometer, you will still be able to see fringes just because the coherence length is so long. And we're working on experiments where hopefully we should be able to achieve a few minutes of laser coherence time, which will be a coherence length of about 1 astronomical unit. And the reason why we want to work on this is because of my atomic coherence time is on the order of a few minutes. And you want laser to be able to probe that. Of course, this kind of laser development can have incredibly useful applications in space science and so on. This is the one example where when the laser was still not so good, people came up with ideas by Pete Bender, Jim Fowler, and so on. of the so-called laser interferometer in space antenna Lise for gravitational waves, where you have millions of kilometers distance between three satellites, and you have to keep that distance very, very tiny, difference to be very tiny, so you can cancel away the laser noise. If you have such a fantastic laser that I'm talking about now, the distance can be further apart, and yet you can still maintain very, very good phase coherence. So let me tell you a little bit of making one stable laser at 1.5 micron. How do you transfer that coherence into a laser that I will use to probe strontium atoms? And this we have to thank for the so-called frequency comb development. If you have a very regular train of pulses in time domain, we all know that by Fourier transform, this will be in the frequency domain, a regular pattern of the frequency components. The shorter the pulse in the time domain, the wider the spectrum in the frequency domain. If it's so wide, you can actually connect directly with a single colored laser to any color you wanted in the visible spectrum, almost like building this gearbox for visible lasers to the microwave or any different visible lasers along this reduction gear. You can think of the frequency comb as nothing. It's a phase coherent reduction gear. For that, I think as mentioned earlier, Jan Hall and Ted Hinch won Nobel Prize in 2005. And our field, in some sense, is amazing. I will go through a number of these fundamental developments in whether you think of this as technology or physics, doesn't really matter. But it's all very new in the past 2 decades or so, and they are all part of the component of building this best atomic clock today. And so this is how fast the field is moving. So of course, the next thing that we need to talk about is control atoms. As we all know, there's a time dilation effect. If you deal with the thermal atoms as they're moving around, there's a time dilation on both factors. One is the moving atoms, moving clocks run slower. The other one is the gravitational redshift. And these two effects will manifest themselves if you are trying to build a clock at 10 to the minus 16 and beyond. So this is sort of a second order Doppler effect, which is an emotional time dilation, this one is a gravitational time dilation if we are near a massive body such as Earth. So this is like a picture of, you have many atoms, each one of them is a little clock, but they're all running at a different speed, if the precision is good enough to tell them to be different. And so this is the technology actually developed in the late 80s of so-called laser cooling, where you can have 3 pairs of lasers coming from 3 orthogonal directions in space. If the frequency is tuned just right, you can actually cool these thermal atoms down to temperatures of a few millikelvin. Actually, in our labs, routinely we can cool down to a few hundreds of nanokelvin in just a few seconds. And in fact, nowadays, we can do that even just in a fraction of a second. And this technology becoming really robust. In many ways, it's laying the foundation for atomic technology forward. And for that, these 3 gentlemen, Chu, Claude Cantigny, and Bill Phillips, won the Nobel Prize in 1997. And yet this is a 30-year-old technology, and yet this now has become a foundational technology. We teach this to undergraduate students. And because of the laser cooling technology, there came very rapid development. One is the so-called Bose-Einstein condensation. The idea being when the atom gets cooled down to further and further temperatures, that de Broglie wavelengths start to become longer and longer until the de Broglie waves of neighboring atoms start to overlap on each other and become a macroscopic coherence start to emerge from these random particles. And if these are bosons, these atoms start to form start to have a phase transition forming a Bose-Einstein condensate. And Cornell, my actually close collaborator now on EDM search, Wolfgang Kadeli and Wyman shared the Nobel Prize in 2001. But the reason I'm saying this is I just feel like there are some members of the Nobel Committee here that tell you that you guys have made a lot of good decisions. For making atomic clocks, this is absolutely, all these technologies becomes the cornerstones of what we are talking about today. And the only person that actually, Debbie Jing reminded me of Lise Meitner. She is an amazing scientist. I have had the good fortune of working with her, but she passed away way too early in 2016. But she was the one who brought us the so-called degenerate Fermi gas. When atoms are fermions, the difference is that there's a Pauli exclusion principle or Fermi statistics. When you make the temperature really low, the atoms start to now very orderly occupying energy level states one by one until they reach the so-called Fermi surface, Fermi energy. And she was the one who was able to create a Fermi degeneracy. And we use now this kind of a technology for our Fermi clock. So this was all really nice that's developing by the late 90s. And I was attracted back to Jella to take a faculty member position in 2000. And so there was something in the neighborhood that's going on with Dave Wineland. He and among others, they were the heroes of controlling single trapped ion. At the time, they were working on single trapped mercury ions, and they were setting records on clocks at the time with a single particle. And of course, he and Serge Harold shared the prize in 2012. And I was really attracted to this, thinking about neutral atom side, we're starting to have a macroscopic quantum coherence of thousands, if not hundreds of thousands of atoms. And yet Dave can do this clock with one. What if we can put 100 atoms together? What if we put 1 million atoms together? We must do better, right? Like I explained earlier about the quantum noise. So this was a dream back in 2000 when I was starting to build a lab. Can we have many atoms working in the optical frequency just like Dave Wineland has, but achieve very long quantum coherence with many, many atoms like this? So the idea came from Arthur Ashkin. He developed the idea of optical tweezers in the 70s and 80s, but he was recognized in 2019 with Nobel Prize, where his idea was I can use optical field to attract atom. That's because you can polarize atom, and so that atom will be attracted to the tip of the laser focus. In general, however, when you created an atomic trap with optical force, the energy states of atomic levels, which I'm relying on to build a clock, will have a different so-called AC stock shift. And so the ground state can be shifted down, excited state may shift it up. And if I trap atoms here, but when I try to probe the clock transition, you can see the clock is no longer going to be accurate. It's going to be influenced by the differential AC stock shift. And so this was actually the idea independently developed by Hidetoshi Katori, working at University of Tokyo. And then at the time, I was postdoc with Jeff Kimball near the end of 1999. And the idea came is building so-called magic wavelength trap, where you tune the wavelength. And thankfully, the atoms are multi-level system. And you should be able to tune a wavelength such that the polarizability of the ground state and one of your clock states happen to match. If the polarizability is matched, then you can keep atoms trapped, just like in ion trap. And yet, you can do clock measurements which won't be influenced by where you are with respect to this ball made out of light. And that's a key concept to allow you to have clock coherence and yet still be able to not worry about this AC stock shift problem. So now you can think of the internal degrees of freedom and the external degrees of freedom can start to be disentangled. Because the trapping potential, yes, it's shifted by AC stock shift, but because they are the ground state and excited state are exactly the same, you can think of these two degrees of freedom are separated. And now you can separately control by driving, for example, ground state to excited state, and you can keep your, if I may borrow the language of phonon, this is actually not accurate, because in this case, I need an atom to be interacting strongly. But in the optical lattice, usually atoms do not interact very strongly. But nevertheless, this is a simple concept that I can think of. If atoms are confined in these harmonic traps, and you can drive the transition from one quantum level, motional, to another motional quantum levels. If they are cooled down to the absolute ground state, you can drive the carrier transition, or you can drive the so-called blue sideband, but you cannot drive the red sideband because there's no quantized states below the absolute zero. So you can see the asymmetry between blue and red. This is physics that ion trappers have already told us a long time ago. But it's really nice to show this very, very clearly in neutral system. In fact, we can cool atoms down now to very low temperatures. You can see these hairy structures. These are not noise. These are actually individual photon recoil splittings. So So we are all set, to start to make clocks. All you need is to shine the laser like I have in my hand, and you just hit a mirror. It will retroreflect and form a standing wave. The standing wave into antinodes, you can attract atoms. So it looks like a two-dimensional traps. If I may use a language like pancakes, you can have a stack of pancakes where dozens or hundreds of atoms or thousands of atoms are trapped in per pancake. And you can start to look at a clock transition by making clock laser propagating perpendicular to the pancake, like this. And what you're doing is, of course, in the fictitious level 2 spin half systems, you're using laser field to drive the spin. As I was explaining, putting the system in coherent superposition, like in the individual Bloch sphere that I showed earlier. These atoms have, in the transverse degrees of freedom, they still have motional quanta. Their states, the motional states are all quantized. So you have a motional quanta N, I, N, J. These atoms are fermions that we learned from Debbie Jing, because they do not interact, the so-called S wave. The bosons and the fermions like to stay away from each other. But if you waited a long enough time, you can see that even fermions, of course, can interact. As we know from condensed matter physics, the fermions can, they just means, with respect to exchange of two fermions, the total wave function has to be anti-symmetrized. And this anti-symmetrization can come from the external degrees of freedom, the motional degrees of freedom, with the negative sign here. But it turns out this so-called P-wave interaction for these Fermi atoms are insensitive to the motional quanta. So you can actually think of all these atoms start to be collectively interacting with each other through the P-wave contact interaction. And that can give rise to a clock frequency shift. And that, in some sense, that's troubling because I'm trying to put lots of atoms in there to enhance the precision. But now I have to deal with uncertainty caused by too many atoms interacting with each other, cause a frequency shift. So thinking about this problem, we actually redesigned the trap to be extremely shallow. This actually happened just over 3 or 4 years ago. We made those traps, those pancakes, to be much, much shallower. So shallow that this gravitational sag has always been there, now becomes very pronounced. So what I mean by this is comparing this pancake versus that pancake, the distance between them is the half of the laser wavelength, lambda over 2. And we all know from high energy physics, there's MGH, potential energy, by gravitational potential energy. The atom sitting here has a little bit higher gravitational energy, MGH, higher than the bottom there. But if you make the trap so shallow, and again, following condensed matter language, this is the so-called Wannier-Stock lattice. There's a lattice, but being tilted by external force, in our case, gravity. When the lattice is very shallow, the wave function actually spreads out. The so-called Wannier-Stock state is actually superposition of the Wannier orbitals. And this individual atoms, it can be think of this wave function is actually spread over many, many sites. And since I have this magical wavelength concept, the ground state and solid state share the same AC Stock shift. Now you can think of the landscape of these atoms now living. The atom and the wave function is spreading out several sites here, and they can interact among themselves in the P wave because they are identical fermions. But when they interact with other atoms from other pancakes, they can interact with S wave. So this interaction allows you the tunability of interacting S wave, P wave together to cancel such atomic interactions. Meanwhile, my clock can still be applied to probe the transition from the same site. This is what I see with laser beams over 3.1 second of a Rabi probing time. This is a so-called Rabi line shape. Or you can even start to probe transitions among neighboring sites. That I meant to show like this. And this comes from the sidebands. And these sidebands are actually experimental data, meaning when I drive the transition from neighboring sites, I'm measuring both the internal degrees of freedom of the clock, but I'm also measuring the external degrees of freedom, which is the MGH. That's why the distance between these sidebands is actually the gravitational potential energy. And so if I were able to take the system even further, prepare atom in coherent superposition like this, and I drive them a few times. So now this atom and that atom is actually, this is the same atom, it's in coherent superposition. Spin up is living 10 stories higher than the spin down. And you let them go, you prepare coherent spin state like this, you let them go, and you can actually measure both gravity and time simultaneously. It's like atom interferometer and a clock built into a single device. And so this gives rise to this cancellation of atomic shift. We have the P-wave interaction within each pancake and the enabling interactions, the so-called S-wave. And I can tune the lattice depth as a function, the interaction is a function of the lattice depth because P-wave, S-wave, their interaction strength depends on the tunneling between enabling sites. And I can get to the point where the interaction exactly cancels the frequency shift. How well I can cancel this. This is where the clock measurements precision comes in. I can zoom in here and see that the cancellation of the atomic interaction at the level of 10 to minus 20 fractional units in terms of the time. So I know this atomic interactions, I can pile up 1 million atoms without having to worry that interaction is going to limit my time, limit my uncertainty. And that's one area where this kind of a quantum state engineering really is helpful. And even though the atoms are interacting, I can tune that away from my clock. So now I can take an image that we understood about gravitational energy. It has nothing to do with general relativity. That's just gravitational energy. Now I can think of, I'm going to take a photo of the entire ensemble of atoms in this vertical lattice. And I'm going to ask you a question. Does the time appear? I'm not looking at the gravitational energy. That has been removed. And what I'm looking at each individual pancake, are time evolved the same or differently? And you can look at the comparison of as if you have two sets of a pendulum. One set is swinging up, the other set is spinning in the down area. And you try to see, you let them go at the same simultaneously, and you watch. Are these still swimming in synchronous? And indeed, after you wait 6 seconds, you can see they're still swinging back and forth in synchronous. There's a little bit of opening. It used to be a line, now it becomes a little ellipse. And if you wait 30 seconds, this opens up more. Something's happening. That's because the pendulum here swings a little faster than the pendulum down there. And in fact, we can actually take this measurement now all the way out to 93 seconds. And this is the coherence time I was telling you about. This two pendulums, this swinging back and forth for a macroscopic time of a minute and a half. And so using this technology, we can actually measure the time difference. But if you think of the clock sitting up there versus clock sitting down here, the clock sitting up here swings a little faster, and this is coming from Einstein's general relativity. And we can measure, the clock measurement precision can actually go down to the mid 10 to minus 21, 6 times 10 to minus 21, taking into account of the total measurement time. As I mentioned, the field is still moving forward quite fast. This was a measurement we made in 2021, published in 2022. But today, just last month, we were already able to push this measurement down by another factor of 3. So it's quite exciting to see how things are coming. But because of that, you can see that we should be able to start to measure gravitational redshift at a microscopic length scale of a few hundred microns. And this is indeed what we did. Back in 2021, we can measure for 1 millimeter difference, the clock shift is 1 times 10 to minus 19. Exactly matching Einstein's prediction, but the point is not really checking gravitational redshift on such a small length scale. The question that I'm really interested in is, as we push this technology further, the concept of time becomes so soft, one day we will be able to see a conflict, because the time over one de Broglie wavelength, the time will be evolving differently. And that will, meaning this, even the linear gravity itself will have a macroscopic impact that we can measure on the many-body quantum states. And I actually have prepared 1 or 2 slides specifically on this. And it's actually something I learned fairly recently. I find it elegant, very elegant treatment, thanks to some colleagues from University of Hanover. And essentially, it's a very simple concept. If you have two-level systems, when the atom absorbs a photon going from ground state to the excited state, the mass changes because there's a E equals to mc squared term. You absorb the photon energy of h bar omega 0, so the mass is actually h bar omega 0 over c squared larger than the ground state mass. And if you write down a single particle Hamiltonian here, this is nothing complicated, right? Kinetic energy plus lattice potential, which is atoms in the optical potential of the lattice, plus mgh, this is the gravitational potential energy, and that's all it has, this single particle potential energy, plus this optical frequency that you put into the excited state. If you just make this mass defect expansion, make a Taylor expansion on that, and you can see this, again, the term that's assuming mg equals to me, this would be, the Hamiltonian would have stayed the same. But because of this replacement of the excited state mass is mg, the ground state mass, plus h omega over c squared, you came up with these two terms. And the first term is nothing but motional frequency shift, redshift, v squared over c squared. It's on the order of 10 to minus 22 if you consider the atoms moving around inside my optical lattice. This effect we should be able to observe if we can improve our clock by another factor of 10 or so, where the motional states lead to dephasing. The other effect is a familiar so-called red shift, gz over c squared term. And because my h bar omega 0 is relatively large in the optical domain, it's on the order of 10 to minus 11 with respect to the rest mass divided by c squared. That means these two effects actually on a similar order of magnitude, and you should be able to start to have very, very genuine general relativity effect, has both motional and redshift effects combined in your quantum system. And I write these equations down didn't mean to ask you to follow these equations, but rather just to say, remember I told you the interaction, I can tune it up by looking at on-site P-wave interaction. S represents the total spin, N represents the sites. And this off-site S-wave interaction with N plus 1 neighboring sites. And then there's a the laser field, it's a single particle Hamiltonian term, but there's an extra term which is coming from GR. That means each pancake evolves differently because of the gravitational redshift potential G times hc over c squared. If you put all these together, this whole Hamiltonian together, you would recognize that the on-site interaction commutes with the GR term, but the off-site term do not commute with the GR term. So you have a quantum system like this. If you have long enough coherence time and a high enough measurement precision, you wait for a little while, you will know that the many-body state is different, whether you have gravity or no gravity. So macroscopic theory of general relativity will start to have impact on microscopic quantum many-body evolution. And that would be fantastic to see in the next 5, 10 years. It's not a quantum gravity. There's no quantization of gravity at the moment. It's just trying to see the conflict of absolute certainty of a GR versus uncertainty of the wave function spread of coherent superposition. This is, of course, really pushing the frontiers of a measurement science, right? Making clocks to go to 10 to the minus 22, 10 to the minus 23 is not easy. And I think one trick that we're preparing is to do spin entanglement. And as I mentioned earlier, if you could imagine you can make n copies of atoms to be entangled, then in principle the noise will be squeezed down to something like this little sliver. And of course, as this evolves over the equatorial plane, it's much easier to determine the time than this big blob of noise when you have uncorrelated atoms. So this is, again, a subject of a Nobel Prize that's very recent, 2022, of quantum entanglement. These gentlemen shared the prize for their work on photons. But of course, in atoms, you have entanglements as well. And these are what the modern excitement of quantum computer is coming from. But from the metrology, from the measurement science point of view, is you're trying to hide noise. You're trying to put n copies of noise into one copy. And that's where you can gain. So, and one idea of doing this that we have learned from Vladan Vulicic's group of MIT, except we use much, much better lasers than Vladan could, is to put atoms inside a cavity, where I also learned a little bit from Jeff Kimball at the time when he was pushing the cavity QED physics in the late 90s at Caltech, is to put a bunch of atoms in the cavity. And how do we do that? Is we make this lattice to be movable. It's like you put atoms into one layer, and you move the elevator up. And this elevator goes up to this podium where you happen to see two mirrors facing each other. And this atom gets confused, looking left, looking right. They see their own face back and forth. And if you have many, many thousands of atoms, they actually get their spin measured in a collective way. And in more technical terms, you can think of a prepared coherence position of the clock states, up and down. And I use the cavity QED as a little spy. The spy can come in to look at the population that's occupying the ground state. So I'm in coherence position of down and up. But if I can somehow, using collective measurement with cavity QED to spy on how many atoms is actually in the spin down state, then in principle, I gain the knowledge. Without destroying all the coherence, I gain the knowledge of the superposition. This is what people call the quantum non-demolition measurements. And on single particle level, this doesn't work. But when you have many, many atoms, the collective physics will allow you to actually hide away which atoms getting the information. Therefore, you can do collective spin squeezing. And we were able to, in fact, demonstrate at a clock of 10 to minus 17 level, the spin squeezing start to work. You can see that we can do better than the classical quantum projection noise limit, where the atoms are uncorrelated versus atoms being spin squeezed. 10 to minus 17 is not at 10 to minus 20. And this, I think, the general statement of the field at the moment, there's a lot of excitement of quantum entanglement and so on. And I absolutely believe in the future, quantum entanglement will help us push the frontier, just like LIGO has. But at the moment, I don't think we have quantum computers outperforming classical computers, just as we don't have entangled clocks outperforming the clocks that I'm talking about without using entanglement. But I'm still using plenty of quantum physics. The very fact of these are fermions, these can be quantized, and so emotional states, and so on. These are quantum states, but it's just not yet in the entanglement sort of a language. In order to push the entanglement to the so-called genuine quantum advantage is, I reached the absolutely best I can do without entanglement, and put entanglement in and did even better. For that, we are all falling short a little bit. But this is the field that we are pushing. We are very interested in pushing this to the next digit and the next 2 digits in the coming years with entanglement. And in fact, some of the key ideas that's coming, it can be very, very exciting. And remember I told you about this vertical lattice, but instead of one cavity, I can make a bow-tie cavity. And now I can entangle atoms from upstairs to atoms to downstairs. And you make this kind of entanglement, and you may start to make a clock measurements. Surely the gravity is going to try to destroy the entanglement, right? Because the gravity is telling you where the atoms are. So this will again be sort of a conflict between quantum physics and gravitational physics. And we just want to be able to get our precision to that level to start to probe these physics. Okay, still have a few more minutes. And I want to tell you the final topic. Again, on the clock side, how do we continue to expand the capabilities to make an even better clock? And this, I'll tell you some stories. Instead of one-dimensional pancakes, it's now three-dimensional optical lattice. If these are fermions, if I can put 1 million atoms into these optical lattices with a coherence time of 120 seconds, back of the envelope calculation will tell you that you should be able to build a clock with a precision of 4 times 10 to the minus 20 at 1 second. At the moment, we can reach 1 times 10 to the 18 at 1 second. If you can get to this level, after you wait for 100 seconds, this precision will be at 4 times 10 to the minus 21. And that's the level of precision you start to be able to see gravitational waves. So it will be quite exciting, that finally the clock can really connect space-time information together to become a more sensitive sensors for many applications. However, building so many atoms into one small package influences quite a bit of these atoms, how you can probe these atoms. You can no longer think of a normal Maxwell block equation can describe how the photons propagating inside a medium like this. This is a very densely packed material, even though it's not condensed matter. The atom is still spaced apart by 1 micron, so still very, very loose from condensed matter standards. But because the precision is so good, the coherence is so good, and the photon coherence is controlled at such a level, when you put a single photon in there, its dispersion relationship will start to be engineered by the geometry of how you arrange these atoms. And I will just go through a couple examples of how we are turning this clock. Here, the clock is almost excused to study many-body physics. And just give you a quick couple examples of this, which is kind of fun to think about. If you put all the atoms in the optical lattice like this, Pauli exclusion principles tells you if you cool the temperature down to sufficiently low level, only one atom will occupy one site. And it looks like just like that. But now, suppose I tell you that these fermions, and it actually has 10 different nuclear spin states. You can think of these as 10 different colors, indicating there's 10 different nuclear spin states. Well, different color, they do not have to obey the Pauli exclusion principle. They are distinguishable particles. And indeed, you can have 2 particles occupying the same site. So that means if you do not do a very good purification on nuclear spins, in principle, you can have doubly occupied sites, which you can worry about clock frequency shifts and so on, other interactions. And fortunately, we do not see that. The interaction is so strong, the interaction effects are very far apart from the so-called single carrier, where it's occupied by a single atom. So the doubly occupied sites are not contributing to any frequency shift because their energy levels are quantized and removed away. The second effect I want to tell you a little bit is, suppose you have a hole, or if the atoms are not all in the ground state, one atom is in the excited state, that will also have problems in clocks. And it's connected also to condensed matter physics. Of course, if you have a hole, this atom can tunnel to there. And that can cause a frequency shift if the lattice spacing is not the same as the wavelength of the clock laser. That would be a Doppler shift. It's a frequency phase difference. But even if everything is occupied, even if there's no holes there, but there's defects, some atoms are in the excited state, this can still have problems. The reason is because the so-called super exchange interaction. This atom will come here, and they will interact with the ground state atom, and they can decide they cannot both stay there, and this atom will be kicked back. And in this process, you're actually exchanging colors. This is actually connected to how quantum magnetism comes in, how different spins arrange themselves. But for clock, this causes a frequency shift. And in fact, we can see this effect. Just like this year, we have this paper submitted to Science where you can see these oscillations. And this oscillation is nothing but the frequency of this back and forth. And this oscillation frequency is very, very tiny, on the order of less than a hertz also. But because the coherence is so good, we can see these very tiny energy scale of the exchange interactions. Another effect that's kind of fun is, suppose you don't have these nuclear spin problem, you don't have the super exchange interaction problem, everything is perfect, and you prepare these atoms in coherent superposition. Well, now each atom becomes a little dipole moment. And you can immediately think to yourself, that you've got a lot of dipole moments connected together, there must be a coupling. And that's indeed true. This is so-called a collective coupling of radiative dipoles. Goes back to the 1950s when Dickey model was established. Superradiance, you probably have heard. And in clocks, we're not looking for superradiance, we're actually looking for collective dipolar couplings will cause a frequency shift a tiny bit. And we can see those frequency shifts as well. And I won't get into the details, but it becomes really interesting that you can actually look at the frequency shift in this strongly, I call it strongly coupled system, but really far from strong because these transition dipole moments are on the order of 1 microdivide, and the cooperative Lamb shift, which are called cooperative Lamb shift, 10 to minus 19 level. The reason why you can think of it as a Lamb shift is the fact that this atom in the middle has many atoms in the neighborhood modifies the radiative structure of the vacuum. And as if the QED have to be introduced to correct for the radiative coupling to the particular atom. And that's why we can call it cooperative relationship. And these effects can be measured now. So it's a very fundamental physics thing that you can turn the clock into a measurement campaign. My final slide really is on yet one more effect. Suppose the dipole is gone. And the dipole is nothing but the Green's function of the one dipole gets in coherent superposition, exciting another dipole. What if I have no dipoles? What if I have atoms just in the ground state? The ground state to ground state atoms can have a so-called van der Waals interaction. This time, the interaction is not because you prepared a coherent dipole. Rather, the atoms are sitting in the ground state, and you can have a vacuum fluctuation when one atom gets virtually popped into the excited state, will induce a dipole on the neighboring atoms, and therefore the van der Waals interaction is 1/6, because it's induced by the vacuum fluctuation. Another thing that reminds you probably is a Kashmir force. The Kashmir force is also vacuum fluctuation. So it's really interesting to think about when you have two atoms. You can think of you move them in and out. It's like the mirrors of each other. They're squeezing the vacuum structure between them. And that's the van der Waals or Kashmir force, however you want to consider it. And the clock can start to allow you to measure these effects at the level of 10 to minus 19 level. So maybe I will stop here. Instead of a dipole pattern, you can actually see the ground state, excited state, they have the same sort of a van der Waals interactions. So I hope you get the sense of, yes, as we push the measurement frontiers forward, that opens up potential new capabilities of a probe fundamental physics. But just to get along, go along the way, there's a lot of interesting problems in condensed matter physics. Condensed matter, in that sense, ego priest, excuse me. But connection to condensed matter, sort of a many-body physics problems, you can probe, you can harness, that gives rise to capabilities of pushing the measurement science forward, yet again, using many-body to come back to help you to build entanglement and so on. And that's really the essence of this lecture, and I want to take this opportunity to thank many great students. They obviously are very happy riding on the balls of the Colorado has a mascot, which is a buffalo, and that they were riding on the buffalo to celebrate their success in the lab. People building the strontium-2 systems, where it's a quantum many-body system with a 3D lattice, building the next generation of stable lasers to push the coherence time out to a few minutes, and building quantum entanglement, spin squeezing directly into their clocks. And I also want to celebrate people who we collaborate a lot. I can't write all the names down, but in particular, Anna Maria Ray has been an in-house theorist who has helped us a lot in between experimental theory, especially she's quite an expert in condensed matter, many-body physics and quantum optics. And we have collaborated with James Thompson, Adam Kaufman on the experimental front, but with many other colleagues, Peter Zoller, Misha Lukin, Mariana Safranova in particular, of calculating atomic structure, thinking about entangled clocks, thinking about grand scale connections to quantum information science, colleagues at PTV, colleagues in just time frequency. And again, thank you for your attention.
Thanks a lot for a very educating and entertaining talk. Before I let you put some questions, I want to say that afterwards, when we have had our questions, we will all go down and have some refreshments. So there's a reception, and everybody is invited to this reception. So, do we have some questions?
Thank you very much for the nice talk. My question is, these entangled systems of atoms and electrons, are they related to lattice dynamics?
Are they related to
lattice dynamics?
You're talking about like a high energy lattice. When you say lattice dynamics, what do you mean? I want to make sure I understand what you're asking. Are you talking about quantum simulation of QCD physics, or lattice dynamics like the lattice I have, optical lattice?
I'm talking about like this solid state physics, condensed matter.
Okay. And then the specific question is that lattice, when you say lattice dynamics, what do you mean? The phonons or?
Phonons, yes.
Yeah, very, very excellent question. So as I was trying to clarify, these atoms, they do not interact strongly enough. Mostly they are in location because of optical lattice. If you remove optical lattice, they cannot form their own crystal. But this can change. We are working on molecules with much stronger dipole-dipole interaction. And one of the, I wouldn't say holy grail, but one of the area we are really interested in is we initially teach the molecules to put one molecule at one lattice site, and then we turn on very strong dipolar interactions. And then you remove the lattice and see if they self-organize, self-stabilize because of the strong interaction. Now you can talk about little phonon. You can probe one molecule here and see how the motional degrees of freedom propagate to the rest of the lattice. At the moment, on the molecule side, we are still keeping the lattice. We are studying so-called spin lattice. The molecules are still pinned to the lattice, but you can flip one molecule spin, and because of a dipole-dipole interaction, that spin can propagate. So it's in the spin degrees of freedom, we can already study this kind of a spin wave. Thanks.
Thank you for the very interesting talk. So I want to ask, where does the main limitation on the accuracy and precision for clocks come from? Does it come from the laser or the atom and the readout?
Yeah, thank you. The measurement precision itself is limited by the laser and atom number. But if you ask about accuracy, I want to go to this slide. So maybe you're asking about, maybe you're asking about this accuracy, right? 8 times 10 to the minus 19. So measurement precision, the more atoms you can have, the longer the coherence you can have, the more entanglement you can have. In principle, you can keep pushing on this. This just tells you how far you can push quantum technology. Accuracy, however, is if I want to tell you how accurate time is, I have to take into account all the factors. In fact, the first thing I'll have to tell you, what is my spatial coordinates? Because a millimeter difference is 10 to the minus 19. And so you can see this start to come in, to become really important to define your spatial coordinates first. The second, at this moment, this 8 times 10 to the minus 19 accuracy that we evaluate, everything else is evaluated at 10 to the minus 19 thanks to this fantastic measurement precision. But there's one thing that's limiting us, is actually black body radiation. Black body radiation is like the most boring thing. It's a single particle physics. But we all know if you do not control at room temperature, there's electric field due to black body of a couple volts per centimeter. And that's enough to polarize atoms to cause a frequency shift. And so, so we actually calibrate this effect by making a true environment of a PBR. Because if there's a thermal gradient, if the black body is not a true black body, then the spectrum changes. Because the atom has multiple resonances, the different spectrum of radiation can cause different shifts. And that's the so-called T to the 6th correction to PBR. So there's quite a bit of work going on. Actually, we spent a year after we got to this level of precision, we spent more than a year to just spending on BBR when we try to push this accuracy down. And that's what's limiting us. And next thing you can ask, why don't you build a cryogenic system around it? And that indeed you can do that. If you build a cryogenic system around this, I think the clock accuracy will go to 10 to the minus 19. And maybe next generation students will do that. It's a complicated experiment already.
Do we have some more questions? Yes.
Oh, that comes a real expert on gravity.
Yeah, well, thank you for a very inspiring talk and also for the special slides for us. So yeah, much appreciated, and of course, really, we are very excited to see the progress in the numbers. So what I was curious about is when with the newest setup you have with the Van der Staar lattice, where you cancel the collisional shifts,
Yes.
like by tuning the lattice. I mean, now we want to combine with also what I'm interested in, so seeing the redshift. So I wonder, at what precision do you think you would need to include the redshift, even in calculating like what the lattice should be to cancel any phase shift? So at what level of precision the redshift will actually contribute to the shift that you get as you start to go up and down the ladder? Thank you.
Yeah, thank you, thank you. This is actually a very intriguing question, and I'm excited to hearing you actually ask that question. What she's asking is actually yet next order. So what you're asking, if I understand it correctly, is the gravitational potential. When I first told you, all the atoms sitting in one level, they're all interacting P wave because those are identical fermions. The particle here, the next level, they're also interacting P wave because they're identical fermion. But between them, they're interacting with S wave. The reason why is that they're interacting S wave is because the laser that I'm probing is not a commensurate in wavelengths with respect to the lattice spacing. Or another way of saying, my laser comes from vertical direction. It puts some phase shift on these atoms, and it puts a phase shift on these atoms, and those phase shifts are not the same. So therefore, these atoms becomes distinguishable. But you can actually find a way, you can actually, if you can make the so-called accordion lattice, where the lattice spacing can be played, and you can actually move the lattice to be exactly the same wavelength as your clock laser. Because my interference doesn't have to be like this. My interference can be like that. And when I interfere like this, I can change the accordion's lattice spacing. So suppose I make them exactly equal, then you will say atoms here and atom there interacting P wave, and atom here, atom there also interacting P wave. And the cancellation goes away. And what you're asking is, well, the gravity can actually make the atom to be distinguishable, which is true. Which is actually like, when I first realized, okay, redshift will change the quantum statistics. It's not a fundamental way, but it's just because we are adding phase shifts. And at the level of 10 to minus 23, these effects will popping up, and you will be able to probe it. And however, I think what you're looking for is the gravitational effect cause the atom to be distinguishable so that it will change the interaction. This effect is further weak, by 10 to minus 26 or so. We actually made it a quick order of magnitude. And I would claim we don't really have the theory, proper theory. What you're asking is how the gravitational field, gravitational redshift coming in to modify the megaparticle physics. And that needs to be, in fact, established in theory. But it's just simple order of magnitude kind of estimate that I can make myself. That effect seems to be even further down the road before we can probe.
Yeah,
I
we
think
have still one
Max has a
question.
question.
First of all, let me answer him first.
Thank you very much. You started your talk talking about connection to fundamental physics, and you actually mentioned dark matter somewhere in the beginning.
Yes.
So how do you see this increasing accuracy clocks being helpful to detect dark matter eventually?
Yes. Yeah, so for dark matter, I didn't get into it. We actually had a couple of papers on it. And so the one way to probe dark matter is it's a connection to the fundamental constants, like a fine structure constant alpha. If the dark matter has any couplings beyond just the gravitational coupling, then perhaps dark matter can couple to electromagnetic fields or couple to the fundamental constant alpha. So by comparing clocks of different species, or by comparing clock to my silicon cavity is measuring the lattice constant of silicon, while the atomic clock is measuring, in some sense, readable constants. And by comparing them, you can actually see that they have a different sensitivities to alpha. And so what one signature look for is comparing these over a long period of time and actually record your data at a very regular intervals. And you can then try to turn this into a Fourier domain and see if there's a particular frequency that you can see a peak pop up. If there's a particular mass of dark matter that's actually coupling to it, then there should be a peak, modulation peak of the fundamental constants. And so far, of course, none of those have yielded anything, but that allow you to put the limits on these potential theories. And from that perspective, I didn't build the clock specifically for probably dark matter, but the dark matter itself is almost a byproduct of this kind of technology. And hopefully, people have been putting forward theories of topological dark matters or dark matter winds as the Earth is moving around. And if you have a clock network, by comparing them very accurately, you might see the frequency differences between, it's like a coincidence measurement, it's like a gravitational wave. But nobody can promise at what level this is going to show up because there's no such theory.
As you mentioned in passing that the definition of the second may change in the
Yes.
future. I've heard this before, and I was thinking, I mean, some 2 or 3 years ago, several of the fundamental constants called fixed values, I mean, Planck's constant, electron charge,
Yes.
this was all based on new physics, I mean, Josephson junction, quantized Hall effect, and so on.
Yes.
But the cesium clock is robust and very die-hard. Is there resistance in the community to change the definition of second because the cesium clock works so well? Do you think?
Thank you. There's two reasons why the time domain change has been so conservative. Actually, it was a life-changing experience. I was fortunate to be invited to this 2018 meeting in the suburb of Paris when the redefinition of kilogram took place. And there's a lot of country, I was there, and along with Bill Phillips gave a public lecture on time, actually. And at the time, people, the only thing that remained unchanged is time. Everything else has changed. And yet time is the most important basis units because you derive all other units from it. So the reason of this conservatism comes from two factors. One, there's a lot of infrastructure for cesium clock. All the GPS, in the end, the clock has to be shared by a global civilization. It's time for humankind, not a time for one country. So everybody has to agree. You have to compare the clocks. The French clock better agree with German. The German clock better agree with the American, and so on with Chinese. So that aspect is we don't have the infrastructure yet. Optical clock. How do I compare my optical clock against the one in Europe? Well, maybe you can have a piece of fiber underneath the ocean. Or maybe there's a technology that we actually have been developing to send laser beams. I prepared a slide, didn't show, that we can now compare two clocks in border by sending laser beams from one building to another over 10 kilometers or so. And you can compare clocks at 10⁻18 level. Of course, when you send a laser beam from one space point A to B, there's an air flowing back and forth. The phase is being randomized. But you have to find the technology by shooting laser beams back and forth to cancel that phase noise, which is doable. And my colleagues have now taken that technology between the two Hawaii islands, that's 10 kilometers apart, and they show this is possible. When 10 kilometers is possible, that means you can go to sky, you can go to satellites. That's because beyond 10 kilometers, there's no air. Once you can do that, then I think it's building up because then satellites can connect multiple continents together to compare clocks. And that would allow us to build a global network based on optical clock. That's the one answer. That's infrastructure still takes time to build. The second, there is a discussion about, even at lunchtime, we had discussion about iron clock versus neutral atom clock. Which species should be taking the place of cesium? And that's a discussion. People have pride written on it. I love strontium atom. Just because I've been working on it. And I'm not a closed-minded guy, but still, that's the atom that I've been working on to find all the pros and the cons. And it is, at the moment, the most precise and the most accurate clock. But you can never be certain that there's not another atom that can come in and do the same thing. So there is discussion in the community of whether you define based on a single atom, or do you do 2 atoms or 3 atoms as a assembly, and take their ratios to define, and with the most accurate clock, for example, strontium to have the heaviest weight. And that approach sounds reasonable to me. You weight according to their specific uncertainty budgets, and in the end, you make a synthetic clock for the whole commerce and a global civilization. And so that's the hope is by 2030, this is what happens. And this also depends on how fast people work together, the clock comparison between different countries and the connection between different countries is actually really important.
Okay, I think this we conclude with this, and thanks a lot for the very
Thank you.
nice talk.